Okay, welcome back everybody, and today we will go over the last section of the whole semester. So after this, the whole semester is gone. Okay, basically we talk about polar coordinates. Which give us some really interesting graph. Okay, we can have r equals cosine theta, which give you a circle. We can have r equals cosine 2 theta, which give you something like this. Okay, like a clover. 3 theta, 4 theta, and we also have something look like this. We try to do the plotting, which is like the butt function. Okay, from here you can see we kind of talk about like why this one is so good in handling rotations and anything circular. Also, we have all these kind of shapes which we cannot circle is okay, but which we cannot describe for these two. We cannot describe in terms of x and y. So this one certainly have its advantages. Then we talk about, okay, since we have something defined, some curve defined in this way, can we do the derivatives, which is a slope line? Turns out we can. Instead of dt, we just do dx over d theta, and you plug in y and x, where x equals r cosine theta and y equals r sine theta, and then just follow all the rules to find derivatives, which is nice. So the only thing left is how to do the integral of polar coordinates. That includes area under a curve, arc length, volume, and finally the surface area. We will be talking about this one and this one today. I gave you the solid formula. Once you have that, the surface area is nothing but the arc length formula times 2 pi r. Okay, depending on how you rotate, you can have r. For dl, you just plug in the formula for arc length. So this one, you get it for free. And finally, for volume, I just leave it for you to figure out. It's basically the same idea with the area. Okay, it's just you need to redo everything you did before in terms of polar coordinates, following the same idea how we did the area. So let's see, how do we do the integral of a polar coordinates? Okay, after that, we will show you how to use that formula to find the area of a circle. And then we will show you how to use the formula to find, okay, the area of the clover, which is not impossible, but really hard to find using x and y. Okay, and then the other significant shape we had only for polar coordinates are the butt function. So we're also going to find what the area here represent. Okay, but that's all tied down to how to find the formula. To do that, let's think about how do we find the area under a curve in terms of x and y coordinates and go back with the idea. Okay, we take the integration, right? AB fx dx. But what you really have is you actually cut this one into a lot of small intervals. Each one is actually your dx. That means you cut your x into small intervals. Each one is dx. And then you kind of have a rectangle here. So every single one is almost like a rectangle, which give you a very short period dx. And here is nothing but fx. So fx and dx really just give you the area of the rectangulars. And then this one basically means put all the rectangles together and take the sum. And then let n goes to infinity. You have infinite many rectangulars. The sum become integration. Okay. So that's the idea coming from how do we do areas under the curve in xy coordinates. Now let's think about how do we do the area of the curve in polar coordinates. For example, something like this. Well, you can guess it's still integration. Before you do dx or dy, because you have x and y, this time you probably want to do dr or d theta. I will propose we use d theta. Dr is doable, but the formula just doesn't look so nice. Now think about what you mean by d theta. What do you mean by dx? Dx means take your x value and cut it into small intervals. Then d theta means nothing but take your theta value and cut it into small intervals. So this is a theta, this is another d theta, this is another d theta. So I actually cut the whole thing into different pieces. Just as what do I do with dx. Okay, that's how I cut my d theta. Good so far? Then what I need to do is, I just need to take every single piece of when I cut the d theta. Okay, I put all the pieces here. I take the sum. And then I let n goes to infinity. That thing become integral. Okay, that will be the idea. Before, when you do the sum here, what you got is actually a rectangle. Now if you cut things in this way, let's take every single piece of them out. What you really have is actually a piece of d theta. That's a small piece of angle. This is the next piece. This is the next piece, right? And then for every curve, if you cut it this way, this will be the shape you're adding together. From here, you can clearly see this is not a rectangle. Then what's the shape of this? Okay. Do you know any shape that both ends go together, plus you have a curve here? That is called a sector. Okay. Is this one particularly a sector? Well, for sector, it should come from a circle. That means R here and R here should be the same, right? From the way I draw it, and depending on the way I draw it, it's really possible that this R here is different from the R here, simply because you don't necessarily really have a circle here. But when you let d theta to be super small, that means these two tiny little things become super close. Then even though they have a tiny difference, when you let n goes to infinity, you can say, okay, more or less, this is a sector. So it's settled. I want to name it a sector. It's not a sector, just like what you have here is not a rectangle. Okay. But it won't matter whenever I start to actually let d theta goes to 0. Okay, so I'm just going to say this is a sector. Okay, then what I need to put here is nothing but the formula of a sector. Okay, and then I take the sum, I let n goes to infinity, it's done. So what I'm missing here is just the formula of a sector. Now I need to ask yourself, if you know a sector, you know the angle here is d theta, here's r, what is the formula of the sector? Try to recall, the formula looks like this, where theta represents the angle in the sector. So in our case, you actually need to do d theta. Okay, that is 1/2 r squared. Well, I want to put d theta in the end. But basically, they mean the same thing. If you wonder where this formula comes from, we can easily do that. Think about what's going on here. The sector is actually nothing but a piece of a whole circle, right? The whole circle has 2 pi. This one will be just a proportion to the size of the theta. So this is nothing but d theta over 2 pi times the area of the circle, because you're only part of it. How big of the part really depends on how big this angle is. If it's 90 degrees, you're 1/4, okay, out of 360, out of 2 pi. If it's like, I don't know, pi, you're just 1/2. So you use the same here divided by the whole proportion, which is 2 pi. You will get the ratio of this area here compared to the whole area of the circle. But what is the area of the circle? It's pi r squared. So pi and pi cancel each other. You got the formula 1/2 r squared d theta. Okay, but either way, we have a sector. The formula is given by 1/2 r squared d theta. Now I let d theta goes to 0. I sum them together. The sum become integral now when I let the d theta goes to 0. Then this will be the formula of the area within a polar coordinate curve. I put the formula here. Note for theta, we start from angle, you end at an angle, so we usually use alpha and beta instead of A and B. But that's the formula. Okay. Let's try some examples. Number 1, always start with something easy, so we know we're doing the right formula. Area of a unit circle. Okay. Well, try to recall what's the formula of a unit circle in polar coordinates. That simply means r equals 1, so you stay on the circle, and your theta can be anything. So that's great, right? Now, by the formula, it's going to be 1/2 r squared d theta. You start from theta, you end at a different theta. To get one complete circle, you probably want to start from 0 and end at 2 pi. Don't do anything more, otherwise you're recounting what you covered before. And then just simply put things here. 1/2 times 1 d theta. This gives you theta over 2. 2 pi, 0. Plug in 0, you got 0. Plug in 2 pi, you got pi. So that's the answer. That's beautiful, isn't it? So easy. Okay? Thanks to this easy formula. If you recall what we did before, if we want to find the area of a unit circle, we actually take this one, we do a trig sub, we end up with cosine square, and we do a half-angle formula, which is a pain in the butt. But once you have some rotation in polar coordinates, of course it's a piece of cake. You can also imagine doing the integration of a triangle is going to be super hard in polar coordinates because it's hard to handle straight things in polar coordinates. But on the contrary, xy coordinates will be super easy if you just care about triangles. Okay, so that's the advantage of polar coordinates in this case when you have a circle. Nice. Now let's try something trickier. Let's take this one. By r equals cosine 2 theta. Okay. But we only want one of the leaves. We have 4 leaves, remember? Okay, solution. Let's draw it. If you haven't done so, again, pause the video, go back and try to draw it. Okay, all these 4 leaves should be identical. My drawing is really bad. But what we care about is what's happening here and here. Okay, or maybe you can take another leaf. Doesn't really matter. Okay, so what's the formula? Well, it's going to be 1/2 r squared d theta. 1/2. Your r is given by this formula. So what you have is cosine 2 theta squared d theta. From here you can see you have cosine square. Pause to think about how to do it. And hopefully after a while you figure out it's going to be a double angle or half angle formula depending on which way you call it. This will give you 1/4 times 1/4 sine 4 theta. Now you need a starting and ending point. You need all the starting and ending points here, but basically the integration part is done. Okay, so what's the starting and what's the ending point? Well, clearly the starting point corresponding to here, and clearly the ending point is corresponding to here. Sounds good? So what you need to do is, from here you can kind of see, you need to know how we generated this graph. You have to do things in exactly the order. To draw the first leaf, you go from here to here. And if you recall what we did last time, that corresponds to theta equals pi over 4 when you finish this. Okay, that corresponding to your cosine 2 theta actually already reached the pi over 2, which gives you 0 radius. Okay, so you have to know this is pi over 4, and this is negative pi over 4 by symmetry. How did we get that? Go back and try to practice how to draw this. So from here you can see drawing polar coordinates or knowing the drawing of the polar coordinate shape is very, very important. Otherwise you won't be able to figure out where is the starting and ending point. So go back and practice, but I'm just going to put things here. Put things here. Okay. What do we have here? We have 1/4. We're missing something here. Ah, yeah. That's why it looks funky. We have 1/4 theta coming from the first 1/4. Let me just take the 1/2. Just to make sure. Let's plug in pi over 4 and negative pi over 4. So if you plug in pi over 4 and negative pi over 4, what you have here is going to be sine 4 times pi over 4 sine pi or sine negative pi. Both of them goes to 0. So the good news is no matter which one you plug in, this long part does not exist. Okay, it's just 0. It's not there. Then the rest is just 1/4 theta at here minus the theta here. So together, what you should have is, where is it? Is 1/4 times pi over 2, which is pi over 8. So the size of one leaf of this is going to be pi over 8. Okay, That's pretty easy to do, actually, right? Great. Now, let's look at another example. Remember the but function? Let's just find the area enclosed by that. R equals 1 plus cosine theta. Okay. And R equals 1. Let's see what we have here. I want to make it a little bit trickier. Okay, for the but function, let's draw it. And we know this is 1, 2, this is 1, this is 1, negative 1. Okay, that's how we draw the whole thing. Now, what do you mean by R equals 1? That means a circle centered at here, going... Wow, my drawing is really bad. Let me redo it. Okay, this looks really ugly. Yeah, this one's no better. Okay, focus here, here. Well, I guess that's the best I can do. Okay, either way. Now, what do you mean by R equals 1? That is going to be this circle. So what do you mean by the area enclosed by these two parts? That's actually going to be the difference between these two. That is going to be this part. Make sense so far? Okay, so how do you find the area of this? Well, if you think about it, if you start to draw sectors, let's say, I can first do this and then erase this. Let's just draw any sector like this. Okay, take this part out. You basically have this, you have this, and you have this. And you want to, the area you really want will be something in between. Good so far? From here you can see the whole black thing is going to be 1/2 r squared d theta, where this r represent, let me put it here. What you really want here is you want 1/2 r squared d theta, which give you the area here. Okay. Then you have 1/2 r squared d theta, which give you the inner. Okay, the inner sector here. So what you really want here is nothing but the difference between two sectors. The bigger sector, which is outside, and the smaller sector, which is inside. So I think it's a natural thing to do, to set up everything, and then you use 1/2 r squared for the bigger sector, minus 1/2 r squared for the smaller sector. And the bigger sector, you plug in the but function because it's outside. And for the smaller one, you just plug in the circle because it's inside. And then you need to start from here, go all the way to here. That is negative pi over 2. Go all the way to pi over 2. Okay, depending on the, whichever way you draw it, you draw it. Let me say it again. Both are 1/2 r squared. And then we finish with d theta. But we want to use the bigger sector, which is the outmost sector, which in this case is the but function, minus the circle in the middle, the closer one, which is the smaller sector, which is 1/2 r squared, but if you plug in the circle here. So together, we have the difference of two of them. Okay. Just to clarify, compared to, for example, the fx and y. If you have two functions, what's the area between them? You use the bigger function, which means it's at the top, minus the one at the bottom. Okay. For polar coordinates, it's different. You are going to have a very outside shape, and you're going to have a very inside shape. Okay? Then you're going to use the outside shape to minus the inside shape in order to get the thing, because every time you draw a sector, you actually use the outermost to minus the inner one. Okay, so they mean different things when you do minus. This one means the difference between two sectors, from the outside to the inside. This one means from the top to the bottom. Okay. So that's what we get here. The rest will just be easy mechanics. 1/2 1 plus cosine theta plus cosine square theta. Okay, minus 1/2, and the whole thing doing d theta. 1/2 and 1/2, they're gone, so what's left will be just this. And the double angle formula for this. So I will just try. Why don't I just put all the details here? To save some steps, I'm going to change this one to 1/2 1 plus cosine 2 theta. Okay, so what you have here is sine theta plus 1/2 1/2 theta plus 1/4 sine 2 theta, going from pi over 2 to negative pi. And together, what I should really have is one plus 1/2 pi over 4 plus sine pi, which is 0, minus negative 1 plus or minus pi over 4 and sine pi, which is 0. So that's what I got, which give me 2 plus pi over 4. Something is funky. That's why. Let me just do this. Okay, so now it should give me 2 plus pi over 4. So that is the area of the butt function, which is cardioid, the outside minus the inside. Through computation, we got this. Okay, so that's it. That's how you find the area of polar coordinate curve. Okay, basically just keep in mind you have sectors. That's why the formula looks like 1/2 r squared, and you need a d theta. You sum them together and let d theta goes to 0. Then the sum become integration. Okay, if you have two of them, use the outmost one to minus the inner one. That will work. So one more thing left, as we promised. That is the arc length. For example, we draw a very interesting graph like this. Okay, now we wonder how long is this from here to here, or maybe from here to here. Okay, and you can easily see it's very easy to do. You just need to put dl there, cut them into small pieces, and you put the starting and the ending angles. For this case, it's starting from 0, going all the way to pi over 4, and then pi over 2. So really, what's missing is, what's the formula for dl? Once you have that, put that thing there, we're all set. Now, how do we do this? Well, the first thing we know is this one equals dx squared plus dy squared, remember? Going from here, if you want to do dx, we do 1 plus dy over dx. If you do dy, we do dx over dy squared plus 1. If you want to do dt, we just divide by dt squared, which gave you this. Okay. Now we want to do for r theta, polar coordinates, we want to do d theta instead. So what do you think? Then the formula look like this. dx over d theta plus dy over d theta, both squared. Okay, which is similar to what you have here, except for you replace your t by d theta because this time you want d theta. So from here we can see arc length formula is really easy as long as you know what variable you want to use. Okay, so now let's talk about how to do this, because this doesn't look simple enough. What really should be here is you should only involve r and theta, not x or y. So let's just do some additional work here. I will take the thing inside out and just try to simplify this part, and then we put it back, and I will show you the complete formula. Okay, but the key is try to take this one, but change it to r and theta. Well, do you know how to change x to be r and theta? Of course, it's going to be d r cosine theta. Then, of course, this one becomes d r sine theta, d theta. Keep in mind, r is not a constant. R is a function of theta. Therefore, you have to use product rule. Let's see how we do it. We do dr cosine theta minus r d cosine theta, which is sine theta. Okay. The minus comes from the derivative, d theta squared plus. Bear with me, it looks complicated, but once we simplify everything, you can see you're going to have a lot of cosine square, sine square to cancel. Okay. dr sine theta plus r d sine theta, which is cosine theta, d theta. Oh, forgot about d theta here. Over d theta squared. Okay. Simplify further, we have the derivative of r with respect to theta minus r sine theta, d theta cancel, squared, plus dr over d theta, which is the derivative of r, plus r cosine theta squared. D theta cancel out. Now what I'm going to do is I'm going to write things up. This one should have 3 terms. This one should have 3 terms. And I want to combine the 3 terms together. Okay. Number 1. The first is dr over d theta square cosine square theta. This one is going to give you the same thing, except you have a sine square theta. So the first term of both things give you this, and as far as you can see, cosine theta plus sine square theta give you dr d theta. So the first one actually cancels out perfectly. The second term is going to be r square sine theta square plus r square cosine theta square. The square from here, the square from here. Together, you have r square sine square plus cosine square give you 1. Plus a third thing. Well, that's the cross term, right? 1 is minus, 1 is plus. The cross term from the first one is going to be 2 dr d theta cosine theta times sine theta times r sine theta minus. Okay. The second one is going to be 2 dr over d theta sine theta, this, times r cosine theta, according to the cross rule. Now, both have dr over d theta. Both have cosine theta and sine theta. And both have r and both have the 2. So, one is minus, one is plus. They eventually cancel each other. Therefore, after you clean everything out, this will be what you need. And that doesn't have x, doesn't have y. It's purely r and theta. So, I put this formula here in the notes. That's the formula you need to memorize. But really, the idea is contained in what we have done before. That is, how do you do this? Okay, when you have dt, you just change it with d theta. Once you finish, you don't like x, you don't like y, but x and y can be rewritten in terms of r and theta, so it's done. Okay, let's try some examples. Let's try exactly the same 3 examples. Arc length, or let's just say circumference, of a unit circle. Then we try the clover, and then we try the butt function. Okay, the formula is given by r equals 1. Now let's use our formula. L equals, circumference means I go all the way from 0 to 2 pi. dl, which is square root of r squared plus dr over d theta. d theta. What is r squared? What is dr over d theta? dr has nothing to do with d theta, so if you take the derivative, it's 0. That is nothing but theta 2 pi 0, which give you 2 pi. Again, for circle, it's super easy. Okay, that's the advantage of polar coordinates. Now let's try this one. Let's find the circumference. Not circumference. The arc length of one leaf of r equals cosine 2 theta. Here is the thing. We have leaf 1, 2, 3, and 4. We already did in the previous example. This is negative pi over 2, 4. This is positive pi over 4. With all that information, our L is going to be from here to here if I'm taking this piece. Okay? I need to have square root of r squared plus dr over d theta squared d theta. Okay. Then what I should have is negative pi over 4, r is cosine 2 theta squared plus dr over d theta. That is the derivative of cosine 2 theta. Don't we just wish cosine square and sine square cancel each other? But we don't have it because this one has a 4. Okay. This is how we set it up. Problem is we do not know how to do the integral easily. So I will actually give you a bonus problem to think about. Finish it, send it my way. This one is nothing but you have one sine square go with this to give you a 1, but you still have this one. I will challenge you to finish this problem by doing how to do the antiderivative of this. So, bonus. Try to do it, send it my way. Okay, this is going to be 2 points. Okay, finally, the circumference of the butt function, r equals 1 plus cosine theta. This will be the last example of the whole semester, so be graceful. Circumference means we want the whole thing, so from 0 to 2 pi. R squared plus dr over d theta square. Do you think this one is going to be easy or hard? If it's hard, we have bonus points. Okay, let's see if we can do it easily. Your r is given by that, so 1 plus cosine theta square. Your dr over d theta is going to be the derivative of that, which is nothing but negative sine theta squared d theta. Let's see what we got. We got 1 plus 2 cosine theta, okay, plus cosine squared theta, plus sine squared theta. There are some good news, there are some bad news. Good news is these two give you 1. Cosine square plus sine square. So we have 1. Converge with the 1, we have a 2. Bad news is, how do we do this? Okay. Do I want to do it? Or do I want to just leave it? I think one bonus is good. Okay, so let's just do this one. Okay, I think the tricky part is you need to realize there is a pattern. 2 plus 2, you can factor things out. Now the harder part is try to recognize this by the half angle formula is going to give you cosine square theta over 2 with a 2. We usually do things in the other way around. But for this one, 2 and 2 together is a 4 square root. Okay, cosine theta over 2, you should have a plus or minus. Now think about your theta. Think about it. Okay, your theta goes from 0 to 2 pi. Then your theta over 2 goes from 0 to pi. For that, you really hate it because your cosine can be positive or negative. It's quadrant 1 and 2. So what we can do is we can actually focus on just half of it. Instead of going all the way from here to here, we just go from here to halfway. Okay, but when we finish, we just times it by 2. So instead of going from 0 to 2 pi, which give me trouble, let's change it from 0 to pi, but then double it. By the way, it's not really bad because you can actually split this one to be from 0 to pi, which give you one answer, and from pi to 2 pi, which give you another answer. Okay, and then take the sum of them. And for each one, you have a fixed sign for cosine. But let's just stay away from that trouble. So pi under 2, pi under 2. Actually, I don't even know if I need to change everything, which one is easier. But let's just do this. Okay. Now, because you did 0 to pi, that means your theta over 2 is actually from 0 to pi over 2. Then it's safe for you to keep cosine to be positive all the time. Okay, otherwise you should have a plus or minus. But worst case, you split them into 2 intervals. Not too bad. Okay, so 2 times 2 times 2 times sine theta over 2. This 2 was from here, this 2 was from here, and this 2 come from the derivative of sine theta over 2, because you have a chain rule. You need to have a 1/2. You need to cancel that. Pi and 0. Plug in 0, you got 0. So plug in pi, you got 8 times sine pi over 2, which is just 8. Okay. So for the but function, one side is 4, but if you double it, you got 8. All right, that's how we are going to do the arc length of this thing. Now, what if I take this but function, I rotate it to get a surface, which is going to be a peach, almost like a peach, or like a complete but function, right? Almost like a peach. Then what you do is you just do 2 pi r, and then dl, but for dl, go back and plug in this. It's really easy to do. Okay, your r, maybe not so easy. Your r is going to be this. Okay, but be careful that your r is going to be this, which is y. But then you need to replace it to be r sine theta to make it polar. Then everything should be safe. I won't focus on that. Okay, because and we won't cover it in the exam. And then finally, what about the volume of revolution, the washer method? For example, yeah, if I rotate this one, I got a peach. Before we did the surface area of the peach, but what about the volume of the peach? Well, it's going to be pi r square. Okay, it's going to be a little bit more trickier to do things in that way. But it's doable. We chose to just skip it because in general, yeah, volume revolution is probably not so good for polar coordinates, because even though you're trying to rotate, which is great, but what you're trying to do is you're rotating with respect to x-axis, you're actually coming inside and outside the board instead of rotating left and right. Maybe, I don't even know that's the right word to say it. But the polar coordinate wants you to rotate in the plane. So that's not going to be easy. You're rotating within with different directions. Okay. Well, that's all. That's all for 10.4, and also that's all for the whole semester. So congratulations, and I won't say looking forward, but hopefully you enjoy the whole class. For this semester, I know half the way things didn't go too well, but this is the first time I'm doing online lectures. If you have any questions, just let me know. And again, I want you guys to feel that hopefully you enjoyed the lectures of this semester. And see you at the final exam, and good luck.